Hey everybody. Uh, have we done a sound check yet? Just to get some voice levels?
We can hear you, Spiff.
I hear you.
Okay. I can hear everybody loud and clear. I think we're good to go. I'll
Okay.
get the stream link soon.
Did you see my question?
Yes, thank you. To me?
Yes, I just asked.
Yeah. Thank you. I just answered.
Okay, good. Hmm.
Welcome back, Bria.
How about now?
We heard you at the beginning, and then you cut out.
Yeah, I heard you, and then you dropped. I can relate.
Yes, you can.
Testing. I see little green things over my head. Can you people hear me?
I can.
We can hear you.
Yes.
Oh, thank goodness. Okay. I will breathe now. Thank you.
I think there's a single space up there. You stand in it. What about your sound?
We'll get started in just a moment, everyone. Kind of making some last-minute adjustments. Well, it's just after 1 o'clock SLT. I think we can get started now. So hello, everyone, and welcome to VWEC's Experts Series. I'm Brayla Genevieve, and today we'll be presenting the best show and tell ever with David Ajuna's 3D Brain Exhibit. And before we begin, please note that our presentation today will be recorded and uploaded onto YouTube. In fact, I believe it is being live streamed on YouTube as we speak. We ask that you please turn off your mic during the presentation until we open it up to our Q&A session. And thank you, Spiff, for putting that in chat. The live stream is in chat right now. So a link to the regular YouTube channel for VWEC is also about to go into chat. As soon as I paste it. When you check out YouTube, be sure to subscribe to the VWEC channel to be notified of all the excellent content that is continually being added there. And with that, it is my pleasure to introduce our guest, who's not sitting next to me right now, is he? I think he's coming right back. I see him. Do I see him? We'll give him a second. And there he is. This is David Ajuna, who is also Dr. David Hubbard. Dr. Hubbard is a research neurologist specializing in fMRI of concussion and meditation. He has a BA in philosophy from Yale, an MA in counseling psychology from Stanford, an MD from the University of Connecticut, and neurology from Einstein Montefiore. He came into Second Life in order to build a brain like a planetarium for neuroscience education, and that is exactly what he's done. It is currently located at Whole Brain Health Sim, but today I believe he is bringing it to us. So fingers crossed that that all works out. And welcome to VWEC, David, whenever you're ready.
Can you hear me?
Yes, we can. Thank you.
Okay. Hello. Wow, it's nice I recognize a whole lot of you after almost 9 or 10 years since this first began. I came here in 2015. Actually, a couple of my graduate students came here at first and met Evan Solstar. We did one of those birthday celebration conferences they have every year, Linden, whatever it was called. And then we came to Wisdom Site, 2016 or so, I think. Wisdom, isn't that about right? Something like that. Okay, well, so I'm going to, my agenda is to talk about how it came about to be trying to build a brain for educational uses in Second Life. So I'm actually going to start with this little drawing, this pencil drawing up here. So I'm going to show you 4 or 5 slides, and then I'm going to ask you to come to the brain itself, the full model, which the plan is to have it right here, but worst case we can have it where it is and teleport to it. But we'll get there when we get to it. So this little drawing is very faded because it is in pencil. And I found this just recently, and I drew this when I was 10 or 11 years old. And I find it quite fascinating. I have not actually looked at it in a long time. I don't want to spend really much time on it, except to say I've sort of been obsessed with the brain and trying to figure out how it works and how to model it since apparently age 10. Let's see, did I do that? The slide just disappeared. Huh. Okay, that's good.
I believe you can push the green triangle, top right.
You go to another slide, yes. Okay, so I want to take a minute looking at this because it somewhat fascinates me and it fits in with where we're going here. Right in the middle of this 10-year-old's idea of a brain is the word good, is 2 boxes, good and bad. It sort of interests me that to an adolescent, good and bad is sort of where the center of the brain is. The very top, there are some hammers. When I was a kid, there were an ad for Alka-Seltzer, and the ad had hammers banging on the person's head. Well, I am not doing that. So this is the next slide. Let's see if I can go back. Good. And then I'm just going to note in the very back are the letters PB, which I know are the initials of my next door neighbor and best friend, Peter Burling, for about 10 or 15 years. So I thought this was interesting, and I have been kind of pursuing this ever since. That was age 10 or 11. I had 3 sisters, and then I got acne. I got bad acne when I was about 11 years old. And it really, it was a very unpleasant thing. I realized I was going to have to find a solution to not being able to survive by being handsome or the best athlete. And so that's when I discovered this lady. Do any of you recognize who this is? Test your microphones too. That's Ayn Rand. So Ayn Rand, of course, has a terrible reputation now, but when I was 13 years old and the book had fairly recently come out, she was the first person who gave me the idea that you could have ideas. It didn't occur to me before that. I thought that was looking in the mirror and running faster than the other kids and trying to get along. And the idea that you could have ideas and have thoughts and have meaning and beliefs, that really kind of woke me up at age 13 or 14. And that pretty much set me on the track to first philosophy and then psychology and then medicine. And so what I'm basically going to do is sort of use these various models of the brain to get us to the final model, which is the one we're going to go look at in a few minutes. So this is sort of the 1600s view of how the brain worked. And it's not so much what's interesting about the actual names that they thought were important back then, such as cautiousness. I think that was kind of an interesting one. But the general idea was that it was a little bit like a muscle. so that the important things would get bigger as if you were strengthening your muscles, the muscles would get bigger. So therefore, if you were strengthening certain kind of brain qualities, that region would get bigger. It would push out against the skull, and you could feel it. You could put your hands on people's heads and know what areas they were well exercised in. But that, of course, didn't last long, and this is kind of the current view. So Elon Musk, he is sure, not only is he going to get to Mars and do a whole lot of great things, he's also going to solve the whole mind-brain problem. And so he already has a device where he can put 1,000 electrodes underneath the skull, lying on the actual wrinkles of the cortex. And he believes that with enough of these little tiny electrodes, he is going to be able to do interface with the brain, do everything the brain can do. And so this whole idea, which initially was called parallel distributed processing, but now really is synonymous with the term artificial intelligence. Basic idea of these brain models is that pretty much every neuron connects with every other neuron, and that then it's all probabilistic. That basically through learning and through comparing and connections with all these different brain areas, that's what happens. Stuff comes in, it all gets analyzed in a parallelly distributed manner at nanosecond rates, 100 trillion synapses, it all comes out. And I think the appeal to this model is that it's super fast, it's unconscious, it's by definition can make every possible connection that's possible to make, and therefore, of course, it's going to be able to have all the answers and to be the smartest possible thing. So that is kind of the current situation in neuroscience, is that it's a massively fast computing system. But that isn't actually what the anatomy is. The anatomy is Broadman areas. So these Broadman areas were determined back in the 1700s. Broadman was a neuroanatomist. And basically what he showed is the cortex had approximately 50 different patterns to it. So the cortex is the thin, rumpled part on the top above the white matter, and it's where all the organization of the complex cells are packed. And there are 50 different patterns in terms of the way these, what those cells look like and how they're connected together. And over the 200 years since, each of these have different functions. So just looking at the one you see in the front, you can see some numbers. In the middle at the top is a pale blue one that says 17. That's Broadman Area 17. I'm going to go back and look at that area in a minute. So what I want to do now is I want us to go into the brain and see these Broadman areas as if it's a planetarium. So we're going to sit right in the middle of this brain and look outwards at these Broadman areas. And then I want to go into more detail and give you a little tour of them, how they work, a couple of diseases like seizures and stroke and dementia, and then come back here and talk some more. So how's that sound for a plan? And then we have to decide, are we going to bring the brain here or TP to it? In fact, we can't TP to it because I think I just took it. Shall I try to just res it here?
You sure can. You're going to need to accept the group tag so that you can res it.
Okay, I think I did accept it, so I should also wear it.
Yes, please.
All right, what's it called?
VWEC management. I can resend it if you're.
Let's see if this is the one. No, that's partner.
Right.
Let's see.
Let me make sure I said that right.
You did send it to me, I think.
Yes, VWEC management. I'll send it one more time. There you go.
Okay. And then shall I try to res it on that that big deck out there?
Let's try, yes, let me go walk over and kind of give you some sense of where Brandon tried to put it, and it worked great. Kind of right out here, and then we'll pull it up in the sky. How's that?
Okay, now so I'm gonna just put it right at your feet and hope for the best.
Okay, my fingers are crossed.
Everybody duck.
Oh, it did go in the air. That's perfect.
And I believe we're still on the same parcel because I can hear you both.
Yes, and you guys should see it. It's right above the slideshow.
All right, so we didn't. It looks like I did not res the oval, the black oval around it. So we won't be able to see it as well, but I think it'll work. So let's see. Is there the teleport inside it? Let's see.
I don't see it, David.
We also don't have a floor, so we can't actually land in it. I think the best thing I should try to do is see if I can re-res it where it was and teleport there.
If it's phantom, we could fly into it and just be floating in it.
Okay, we can try that. Where I am, we are inside it. That might be a fun little, adventure. Come fly to where I am. I'm going to try to get myself on top of the amygdala. We should be afraid of our situation.
Okay, if everyone would like to stand up and fly up and back, we should be able to get right in there. It is phantom, so we should be able to fly right into the brain. Let me know if anyone needs any assistance.
Good job, everyone.
Well, it looks as if, oh, here we go. Okay. So I'm going to light up different structures just to give you a sense of where they are. So I'm going to move myself flying between the two amygdalas. So these structures here, these round balls right underneath, right where gentle heron is, these are the amygdala. So I think it's kind of always interesting to realize what these structures look like. So first of all structures are bilateral, so we have two amygdala. The amygdala are actually not part of the cortex, they're part of the subcortex, the archaeocortex, and their job is to let us know what is unfamiliar and dangerous. So everyone talks about them as being where fear is. Actually, they're the area that lets us know that something is unfamiliar and dangerous, and then the fear happens in a different part of the brain. But this is the structure that does that. Oh, the frontal lobes are now in front of the amygdala, and so here are the frontal lobes. This is the part of the brain that is where all the motor action is. So basically the brain is sensory in the back and motor in the front, And so these are the large motor structures in the front of the brain, the prefrontal cortex. This is where planning is and all sorts of putting together complex behavioral and motor tasks. I'm kind of going to do an overview and then zero in. So now I'm going to fly upwards because I'm going to fly up to the motor strip. So the motor strip, these neurons up here, way up at the very top of the brain. Some of these motor strips, some of these neurons are 2 or 3 feet long. They go all the way from here down through the brain, through the brain stem, through the spinal cord, where they synapse and go out to the spinal cord. So these are really long. In the giraffe, they're even longer, of course. These are where those neurons start from. I'm not going to go back down again and show you addiction. So basically, the structure you're looking at now, sort of having to follow me around, but I am now in the basal ganglia. So Gentle Heron and I are in the basal ganglia. What we're looking at are 2 sides of the 3 different parts of the basal ganglia, the putamen, the globus pallidus, and the dopamine system is. So this system is the dopamine system. This system's job is to move us, is to motivate us. If this system wasn't here, we would not move unless something was dangerous. It's this system that says, I want you to move forward. I want you to seek food. I want you to to explore. And the opposite is the real problem, which is if one is not getting what one needs or wants, that's what withdrawal is. So withdrawal is that very unpleasant sensation that one gets when one is not getting what the system thinks that body is needing. This is the hippocampus on either side. So this is also a subcortical structure. Wisdom is right between the 2 hippocampi. I'm going to move myself over there too. So this is the structure we always think about when we are talking about memory. Though in fact, this huge structure is also old cortex. It's not neocortex. And so really when we say memory, it's actually place memory or spatial memory. It doesn't hold our memories of what we see or what we hear. It holds a very accurate memory of where exactly we are, including our orientation, up, down, sideways, and our perspective. Are we looking at the lake from the shore, or is our vision of that memory looking from a boat toward the shore? All of that is handled in this structure here. I'm going to come back to it because I'm going to show you what Alzheimer's plaques look like, because Alzheimer's plaques occur in the hippocampus. I'm looking for my menu there. Okay, so now I'm going to sort of challenge myself. So this is what I am working on now, is how memory and remembering and seeing work. So I'm bringing you back now to the visual cortex. So I am between the 2 sides of the visual cortex. This is a good one to really fly around a little bit. If you go way up and then look down at the brain, you will see how huge this visual cortex is. It goes from the back of the brain and kind of wraps around the back of the brain. So what I've done to make the point of this is I put onto, actually Galen, with Fran's help, put onto this mesh. So this is a mesh from an actual MRI scan in the Netherlands, University of Maastricht in the Netherlands. We imported actual MRI scans in a format that's called DICOM for medical imaging. And then Galen used Blender to transfer them into Second Life objects. And so these are actual real Broadman areas, and this is the visual cortex, which is a very intense mesh. So we made it a little more legible. So if you can look closely, what you're going to see is snow. So on that we have attached textures of snowy scenes. And I want you to see if you can actually see that, because I'm going to make a point about how seeing and memory works. So this is the part of the brain that sees. If we were standing in a snowy environment and looking out at it, that scene would come in our eyes, it would relay through our thalamus, and then it would hit the middle layer of the sensory cortex, so-called layer 4-5, or the mid-layer cortex. I didn't do that, but let's see. I'm going to see if I can get it back again. Well, maybe I didn't turn off the option. Make it locked. Okay, so now what I'm going to do is I'm going to show what happens when we have a memory. So if we were standing on this snowy situation and looking out at it, this part of our cortex would be all covered with this activity. We would be seeing it in the present moment. But now we're going to leave that situation. So what I'm going to do now is I'm going to show, okay, now we're somewhere else. Now we're in another place. So now what I'm showing is that same structure, only if you look closely, it's a fall scene. Those are the brown and oranges of fall foliage. And so the idea is that this is what we would be seeing if we went to that same place in the fall. That same part of our brain would be activating, but it would be a different memory. So in a sense, this is the fall memory. And if we were having, if we were thinking, if we were either in the winter scene or if we were remembering being in that winter scene, then we would be having the other memory. We would be having the memory of the winter scene. And so that is what I'm trying to kind of communicate with this way of looking at it. Now I want to just show, so I've given you a sense of anatomy, and now I want to talk about a few illnesses to give you a sense of why anatomy is not all that matters. So the first thing I'm going to do is show you what Alzheimer's looks like. So let's see. Quite right. So that actually is a histology of an Alzheimer's plaque. So for some reason, it's sort of not quite the right color. But the idea is I'm able to put onto these brain structures what the actual histology under the microscope would look like. So that's what this actually is. I can put any sort of histological microscopic texture attached to these structures to show that idea. So now I'm going to show you an example of seizures. So what would a seizure look like? So let's see if I can get this to work. Yay! Okay, this is Fran's modeling of a seizure. So what this shows us is that seizures arise in one location. We're going off too quickly, but they arise in one location and then they spread out across the brain in all directions. So I'm using a particle system to try to demonstrate that brain disease, which is that pattern. So for instance, now I'm going to show you a stroke pattern. Let's see if I that one. No, not that's quite what I was. There we go. So this is meant to be showing emboli coming up, say, from the heart or from some other part of the some vascular system. I saw them for a moment, but now I'm not seeing them again. So this is a work in progress on how to make this brain be useful to show other things besides just the anatomy.
David, there was a question, and I'm pretty curious about this myself. Dee Dee was asking.
Go ahead and take questions, and also we could do it from back in the at the other side if we want.
Up to you, whichever you would prefer.
I think we're fine.
Well, the question was about the seizure, and they were asking if the seizure always sort of starts in that same location and spreads out from there.
What a great question. So that's exactly right. So a seizure starts from wherever the scar tissue is. So in this particular example, which I will see if I can show again, just for fun, I had it coming out of the middle of the brain, so it could go out in all different directions. The most common locations are actually rather in the middle of the brain, the so-called medial temporal lobe, but anywhere there's a scar tissue can be the source of a seizure. I'm quickly scanning nearby chat or whatever to see if I can answer anything else here, or else we can go back to the sitting area. If people will get seasick in here. Sorry, we don't have
David?
the
I'm
dome
here
around
now.
it.
David, I'm here now. I'm so sorry.
Oh, hi, Fran. Hi, Fran. Well, I think we're done. I tried to just take it myself, and I didn't take the whole thing. I just took the brain.
I know it. It's totally my fault. I didn't make it here in time. I could show the dome if you want to show that now.
I don't think we need to now. I think why don't we sit down and see if there's any more questions.
All right.
Thanks, Fran.
All right. So sorry.
All right, then, if we want to, we can. Exactly. Let's head back to the seating area, and we can address any questions y'all may have.
Really, you're right on top of the Alzheimer's plaques now. So maybe Fran got that working for us. So that's a more accurate color. Those are the hippocampus on either side of you and me, Bella. And then that's a more accurate color of what the Alzheimer's plaques look like if you're looking at them under a microscope. Now I'm heading back.
All right, so we're hopefully all back in the seating area. In just a moment, I will give everybody a landmark to where the permanent exhibit is located in the Whole Brain Health sim. So we'll have that in just a moment for you. But this would be a great chance if you have any questions about the model or about brain anatomy, neuroanatomy, let's have it.
And Ram. I think the message that I try to communicate is that this idea that the brain is just a computer is really misleading. And even the ones who talk about it that way, the actual physicists and neuroscientists, et cetera, they really don't mean it quite that way. So I think the point that's important to make is we are not unconscious nanosystem computations calculating probabilities and making us do stuff. That's not how our brain works. We actually experience reality. So that visual cortex example I was trying to show you up there that's actually hitting our cortex. That's not computation. That's the direct stimulation of those cortical cells in response to the peripheral receptors coming in from the outside. We are not living in a hallucination. That's kind of a popular YouTube topic these days. And I wanted to make the point about my troubled childhood, that since age 10, I've been sort of obsessed with this stuff.
has a question. Would you like to ask your question in voice?
Well, sure, but go ahead and ask Wisdom Seeker. Wisdom Seeker asks, what does meditation do in the brain? Because mine's going to be a little off topic. So let's answer that one first.
Okay, I actually don't see that. So, what is meditation? Let's see. Meditation quiets the brain. I think there's still, after all these years, there's still pretty much agreement on that. Now, the question then becomes, what does quiet the brain mean? And so it doesn't necessarily mean empty of activity. So there typically is when one is meditating, there typically is an alpha rhythm. So that's a resting state pattern. But basically, it's not thinking. Meditation is either using a mantra or some other method to either focus or try to not focus so that you are having less thinking activity. That's what meditation is. So it would be a quieter brain, but not a silent brain. Okay, I'm reading yours, Max. Yeah, Max, there's this disorder that's being talked about now called aphantasia, which is getting a lot of attention, and no one's really quite sure what it is. But it seems to be, it doesn't quite fit, but there's a wide range of these kind of variations. And this is a group that seems to be able to experience everything normally, but then their memories are no longer in color. So even though they see everything normally, they don't remember it in color. And there's every possible wide range to how that happens. And so let's see, what is it you're specifically verbal language? So, I mean, we have to ask ourselves, what is language, of course? And I think a smart way, Chomsky, of course, said language was innate to our brain structure. And that really, he just couldn't make the case for how that happened. It makes more sense to think of language as essentially a very special kind of, to think of a special kind of memory. It's memory without the specific memories of how we learned it. I don't remember where I learned the letter A, but at some point in my life I did learn it, and now all of those letters we can use, all of those symbols we can use without having to be tied to whatever the initial memory was that we once had. So basically that's what we mean by thinking. We're talking about the use of language. We hear them in our head, so that's what thinking is. It's listening to the little fragments of words that are going through. I think most people those would be auditory words going through our minds. I think some people think they also have them as seen words. So basically we have what we see now, what is going on now. We have our memories of such experiences that we've had in the past. And then we have the words we use to analyze those memories and those experiences and try to come up with new ones. And we do that sometimes being afraid through our amygdala and sometimes being driven through our basal ganglia dopamine systems. And that's us.
Any other questions out there?
Well, I was going to take us a little different direction, and I have to just say, David, this is so incredibly interesting. Thank you for all the information. I've been to your presentations before, and this is just such an interesting topic, and I don't want to get everybody sidetracked from it, but I kind of wanted to go a different direction and ask you about why you chose Second Life, how the build manifested. I know Fran has helped you a lot. I'm happy for Fran to jump in, because actually there's probably a lot of people sitting here who are educators who want to teach something, and your model is spectacular. When I've actually worked with folks at my med school, and they've talked about the power of walking through something to learn it versus just seeing pictures of it, or even a brain that's laying on a table that you're dissecting. So could you talk about why you chose to build it?
Yeah, that is a very fun topic. I have been sort of trying to build brains since I was 10, but also as I went through medical school, I also found it very helpful to try to build something, to kind of put things together and maybe have a wire that goes from a thalamus to a cortex, so I can visualize it that way. And so with the cortex, it's particularly a challenge because to look at it as a two-dimensional structure, you just cannot get a feeling for how big those structures are and how they relate together. So I said, okay, there ought to be a way to do it. I knew that MRIs have a definite image suffix, it's called a DICOM image. And so it seemed like it ought to be possible to be able to import the DICOM images from real MRIs into Second Life. So I found a University of Maastricht in Netherlands who was able to do that. It was a company I'd worked with before, Brain Voyager at the university, that actually made structures for fMRI research. And then I found Galen through Wisdom and Fran, I think. I needed someone who knew Blender. Is it Blender or Bender? I never get it straight. To convert those three-dimensional images into Second Life images. And that was a major project that took a long time. But now they're there. So those 50 Broadman areas are in a script file. And so I can open them up anywhere, and they're all linked together in the proper location that they were in when they were in the brain. And so what I did next is for each one of those, I put labels on it, I put tags on it, I attached a little text as to what that structure did. So that text is in the local chat. It turned out it kind of drove people nuts to have it taking over the local chat, so we don't use that part of it anymore. And then I also put together the slideshow that would go with each of the brain areas. And then the trick was to how to get inside it and make it be an experience on the inside. And so that's when we started having it on the inside. And people like that. People like going inside, seeing it from the inside out.
So about how long, do you mind, did it take you guys? It sounds like you had a team of at least 3. There was some Blender knowledge needed, but I see Hubbard text, and I heard you talk about scripting. So these are basic virtual world tools that you just managed to use so nicely. About how long?
That's a good way of looking at it. Yeah. So when you first come to Second Life, so how did I pick Second Life? There was one other alternative that my son knew about that seemed to be more of a building buildings or something. You probably know what it is. That was back in 2015. So it seemed as if this was going to be the obvious place to do it. Of course, when you first join, it took me weeks just to walk, just to go in a straight line. I think it almost took me 6 months before I could even get basically around. The next thing I did is I went to that Builder's Brewery, I think. There are places where people love to build stuff, and some of them, depending on how big a project, you can pay them to do it, but things are very cheap in Second Life, it seems to me. So I fiddled around with that. I got together with a German woman, Biru, who knew more about it than I did. So we were able to kind of scrap together pieces of it. But it wasn't really till we found Galen at Whole Brain Health that we started getting the team together that could do the whole thing. And so it's been since 2015, really.
I think there's a great takeaway there regarding having a vision for sort of an interactive exhibit as opposed to, like, I like to create, 16th century buildings and artifacts from that period. But it does take more than just, hey, I know what it should look like. I have to also know how it moves and if it makes a sound. And you really need a team to come on and help you with the scripting and with the audio and with everything else that goes with that in order to make that fully immersive experience.
Looks like Fran has added his part in that, though I'm sure it's bigger than just a few sentences. Would you like to talk about
right.
that?
Fran did all the scripting. That's right. So Galen brought the DICOMs from the real world into Second Life, and Fran did all the scripting for all the different parts. It's linking them all together, the menus, all the pieces.
Well, a few minutes ago, I handed out to everybody the landmark to go to the original structure. And David, you didn't take that down, did you, to bring that over here? Did you?
I did.
Oh, okay.
I just took it. I know how to hit the take button. That's one of the buttons I've learned.
Okay. Then maybe at some point soon, if you guys want to go visit that, you certainly can. Hang on to that landmark. Give David a little time and his team to put that back together so that you can visit it. It's very cool inside the black dome that he has it in, because unlike here, with the black background, you can see all of the different components much better. You can also see all the little text areas that have been included there, so that you can see the different parts of the brain in action. A brain hat, yes. We need to make a brain hat, a souvenir brain hat. I think would be excellent.
Have one. I'm gonna give it to you right now.
Bren is offering to res a copy of the brain. What would you think of that, Ellie? Is that something we could do?
Oh yeah, he's all set up to do that. David, do you want to take yours? And then he could res the one with the black around it. It might be a little easier for people to see.
Fran, and also we're going to need something back there because I took the one there. So can I have you make it? I'm going to get rid of the one there now, and then will you also put one back? The whole brain health. So I'm going to.
Yes, I just
see the brain. Did Fran take
I just sent it back to you, David.
Okay, thanks, Fran.
Yep, I'm sorry. Let me find the one that I had. Okay, here we go.
Nice.
That's what it was supposed to look like. So.
Yeah, nice. I love that.
Oh. Wait a
Death
minute.
Star.
Wait a minute. Why didn't the... Okay. Sure.
That's no moon.
Nice. Oh, that looks great.
Yep.
You can see the snow in the visual cortex at the back. Oh, the slides work too. Excellent.
Yep.
It's good though. All of us educators get to see the traumas of putting these things together and getting them all to work.
For sure.
I threatened Brila with bringing my carousel of 35 millimeter slides.
Yes, I've heard rumors of projectors and carousel slides like that. I've never actually seen this sort of technology. It's completely foreign to me, she said sarcastically.
I hear you. I see you, Serenity. Go ahead, ask your question.
Serenity is asking how easy it is to damage the brain. For instance, you said that seizures begin at the site of scar tissue. Does that mean that seizures due to, say, low blood sugar are causing enough damage to the brain to cause scar tissue?
Wow, great questions. Okay. I've been on the phone with my nephew, who is a soccer player in Chile on one of the lower level teams, and he was knocked unconscious and had no memory for an hour before and 3 hours after, and then was very dizzy and couldn't really do anything, barely even walk for 2 weeks. So it's always really scary. So we were WhatsApping each other once or twice a day for 2 weeks while he was down in Chile. So usually when we bang our heads, we are twisting our brain stems. The top of the spinal cord is the brain stem. That's where our vegetative functions are, including the sleep-wake cycle. So if you twist that structure, it becomes a little bit swollen, and that's what causes a concussion. That's what a concussion is. So in general, because it's only swelling and it's only a twisting of that structure, in general, people recover. So it's not the concussion that's really what the worry is. The worry is that the brain up above the brain stem, that's getting damaged. So that's what got figured out with football, is that it wasn't so much the concussion itself, it was the severe trauma to the brain cortex causing some bleeding along the edges of the brain, as well as the twisting of the brainstem that caused a concussion. So that kind of really confused things. It wasn't the concussion that was really was horrible for the person at the moment, but it was the trauma of the brain. So then, how does the brain get traumatized? And it really gets traumatized pretty much the way you can imagine a bruise on your skin. It's going to have blood coming into it. The blood's going to dry up. It's going to be a bruise. There's going to be swelling. In general, that will recover. But sometimes, just like skin, if you've banged yourself hard enough, that tissue can be scarred. So that's what trauma is. That's the kind of the trauma that one gets with an accident, which of course is, and so some of those will have scar tissue, and then some of that scar tissue will cause seizures. One can also be born with a little bit of scar tissue, so there are congenital seizures as well. And then once there's a little area of seizure, that area is electrically less stable, and if that starts to accelerate, then the electrical signal can spread across the whole brain. And when that happens, all the neurons that are passed by that spreading electricity are going to fire. So that's why you get, in the movies, you'll see the person whose all four extremities are shaking. That's because the electrical activity is going everywhere in the brain. And among other places it goes through the brainstem. So that's why people in general are unconscious during seizures. If you only had a seizure of your right hand only, so only the scar tissue was only in the area of your right hand, then your right hand would shake, but you would not be unconscious. Once the spread of the seizure goes across the midline, that means it's going on both sides, which means it's going through the brainstem. So that's why you get unconscious. So when we think of seizures, we think of the person being unconscious, though they don't have to be unconscious. The scarring doesn't interrupt normal transmission per se. So for instance, there are types of brain tumors that just push the brain out of the way. They are essentially scar tissue themselves. They grow. The brain just moves out of their way. They never actually interfere with any of the neurons of the brain. And then there are the type that are invasive, and they can go in amongst the normal brain cells and cause damage. So really, both ways are possible. The two most common illnesses that we think about are Parkinson's and Alzheimer's. Parkinson is a gradual loss of dopamine from the cells that make dopamine. Dopamine is the system that makes our movements be moving toward a certain direction. So there's a kind of a motivation component to the movements. And then Alzheimer's is the hippocampus, the part of the brain that helps us store and retrieve memories, gets damage to it in the form of amyloid, which is a protein that accumulates and causes what's called a plaque. It's not technically a scar tissue, but it's like a scar tissue. So the most common brain damage would probably be Alzheimer's or dementia. That's a good slide down there. Can you see the brain from where you are? I'm sort of zoomed in on the brain inside. Those are pretty good slides there. Should we call it a day?
We can. I do have a few closing remarks to make. If anyone thinks of a question, this would be a good time to get those in. So our next VWEC Expert Series continues February 24th at the same time, 1 p.m. SLT, with Brent Knudsen, who will discuss how to integrate virtual world learning experiences into your curriculum. And you can find this and all scheduled events at the VWEC Events Plaza calendar, which is just over yonder, and also in local chat, which I am putting in right now. And as a reminder, YouTube for WVEC, our channel can be found at this local this website that I'm also putting in local chat. And finally, oh, don't forget to subscribe to that channel because it's becoming quite a resource. And finally, if you're interested in presenting at the VWEC Plaza, like Dr. Hubbard has today, we have a form that you can fill out online, and I will put a link to that also in local chat. And that's about all I have. Does anyone want to slip in a question real quick before we call it a day?
Thanks, everybody. That was fun.
Thank you so much for being here for this awesome presentation, and I was not kidding when I said this is the best show and tell ever. Am I right? Thank you all for coming today. Y'all have a great afternoon.
Thanks so much, David. Thanks, Fran.
I'll go ahead and take the brain back now.
Oh, thanks, Fran. It looks so easy, and I always screw it up.
You did awesome. I think we had a great time running around the brain, flying around the brain, maybe.
It's fantastic. Yeah.
And we appreciate all of you guys because you are so patient, and it's always worth it, but we appreciate that you guys roll with the fun we have. Thank you, everyone. Oh, absolutely. Bring your students to see it.
If you'd like to join us on the deck just behind you, we can go ahead and have a bit of a social if you'd like to chat for a bit.
that's interesting, Liz. Do you want to tell us about it? So it started with friends, huh?
So it actually, so Ewan and had classes here, and he was looking around at the Second Life birthday celebration and saw the brain and told us about it and connected us with the people. Well, at the beginning, actually, David was not involved. It was more the people. He had two graduate postdocs in psychology working with him who came really over to us and created that first brain. So we had a number of events with Science Circle and other places where people came, and they talked about the brain, explained what they were doing with it, and we used it in various events to try to show the connection between parts of the brain and activities that people do. And David was constantly looking for something that would create more of an active brain that was closer to he especially wanted the basal ganglia in the brain, and he couldn't get them with this. So he worked for the university, and Galen brought it in. She works with Blender. And so he was able to do much more. He's added parts to it that he couldn't have before, so it's become more and more accurate, I guess you would say. And now he's working more toward actually having the brain be active in various ways. So it's an evolving kind of project, and I think it's really important for people to start with where you are, simple idea, and then keep developing it as people show an interest. I think one of the big things that David really is looking for is to have people express that interest and have it be used more. So that's why I'm saying if you have classes you can bring in, please do, or if you know other people who might be interested in coming over for a talk about the brain, I think David would really find that to be very, very, exciting and satisfying. So if we can find other things to do with it, you please tell us. We try to help him as much as we can, and we try to make sure that these things happen. Yeah, Val, that will help. So, as I say, if you know other people who you think might want to come and see the brain, or you have him bring it over or whatever, let us know.
Thanks, Liz.
That before was literally a large version of what you're wearing on your head right now. It's a sculpted representation that one piece, so that you can't see the individual parts, but it was made to look like a brain. And we, as Liz said, there were platforms inside that people could go into, and there were areas that would light up, just similar to what you see the lights going off here, but they were intended to be lights that went off at specific points in the brain to illustrate what he was trying to do. But it was a very rudimentary play that he, like as she said, he was not really satisfied with, and so we came up with this new brain that does have the different areas, Broadman areas, that he wanted to try.
Well, I love hearing it. Oh, go ahead, Fran. I'm sorry.
No, I just wanted to throw in that this brain hat that we have is actually a relic of the old brain that he put together.
A legacy brain. Well, and I love the hearing the steps, because I think a lot of us feel like we have to get there the very first minute